Okay, welcome back. We're going to talk today a little bit about design, and I really like to pause our learning a little bit and apply some of the things that we have learned in the various videos we've seen so far to actual design problems. And I think that's a bigger part of learning sometimes, is actually taking what we've learned in the discussions and then applying them to an actual design. So what we're going to do is we're going to start exploring the idea of designing a 7-segment driver. Now, 7-segment drivers have been around for a long time, and they represent a really neat synchronous sequential system that will help us explore VHDL a little deeper and get a little better idea of how to design with VHDL. So the way before we start diving into the 7-segment driver, let's start talking a little bit about some fundamental concepts of the human eye and the fact that we take advantage of it in some of the devices that we use every day. So if you've ever been to let's say a camp, and you've had a campfire going, and as part of the campfire, you take a stick and you stick it in the campfire and you get it all hot and where it's really, really bright. Then you take the stick out and you kind of wave it around in the air in the dark. You can see kind of a trail. It leaves kind of a trail behind it. That's because of the way the eye reacts to light, and the fact that there is a persistent perception of the light even after the light goes away. It's called persistence of vision. And the idea is we can show something temporarily to you in the eye, and then when that goes away, you still see it slightly. It still registers there in your brain that it's there. Think also of looking at a bright light and then suddenly flipping that light off. You can still kind of see that light there. So we can take advantage of that characteristic of the eye, and we can use it to reduce the amount of power we consume on some devices, and also to basically reduce the number of wires that it takes to interface those devices. So one of the things that I'm talking about in particular is a 7-segment display. Now, basic 7-segment displays basically have 7 segments arranged in a pattern similar to the one that I'm showing here. And in order to demonstrate a number, produce a number, we will light the various elements of the 7-segment display to give the illusion of a number, a numeric value. Like this could be the number 7 by lighting those various elements of our 7-segment display. Now, each segment, and this basically right here is a segment, represents an LED, or is an LED in the device. And so we have 7 of them here. That's why it's called a 7-segment display. And all 7 of those things combined together will represent a number. We've seen this in electronics everywhere, from alarm clocks to dashboard displays to, it's a very common way to show numbers, numeric values. And so what we're going to do, though, is show when we have multiple elements of this. So let's say we have our 7-segment display like this, but we have a bunch of them, right? So we can have, we have another one here, and then we can have another one here. And so in effect, what we've done is we've created a bunch of 7-segment displays that we want to then display a number like 276, right? We could display that on our 7-segment display. Now, to do that would require an awful lot of wires for our hardware to interface, right? So if each one of these LEDs required seven lines, that would mean 7, that's 7 times 3, 21, so that'd be 21 lines. So that's 21 wires. If we had 4 displays, right? So if we put 4 displays, that would be 28. So we're starting to get into a lot of wires just to light up a few LEDs, and that seems kind of crazy. So what we do is we take advantage of the persistence of vision that people have, and we basically only light up one at a time. So we'll light this one up, and then when that goes away, hold on a second, I've got a new tool that I can use for us. There we go. So if we light this one up, then when that goes away, we'll light this one up. Then that one goes away, light this one up. That'll go away, and this, and that'll go away. Then back here, and then here, and then here, and then here. So you get the idea. So we're constantly cycling through the displays, but we're only lighting one up at a time. That means we can get rid of a lot of these, right? So we can remove a lot of these wires, and we can only just use 7. Since we're only lighting one at a time, that's only 7 wires for each digit, and then 1 wire for each of the displays to activate one at a time. So we would have 4 wires maybe coming from here to activate, and then we have 7 that are shared between all of these. So we could share the 7 here, and that would give us a total of 7, 11, so 11 wires for doing a 4-digit display. That does require some, hardware to scan the displays, to go back and forth and only activate them one at a time. We have to drive them at a rate that the human eye won't perceive that they're flickering. So we would typically, the way we typically do it is like around 1 kilohertz. That's a pretty good rate of display. So for every cycle of a kilohertz clock, we'll change to the new display. And so that pretty much creates a nice solid display for people to see. It looks like they're all at once, but they're actually lighting up one at a time and scanning the displays. So like I said before, this gives us a lower wire count. And by the way, a lower power consumption, because we're not driving them all simultaneously. We're only driving one at a time. So that's kind of a nice advantage there as well. All right, well, let's see how this thing looks. And the best way to understand how it looks is to first off see what the heck is inside one of these individual displays. And like we said before, the only thing that's really inside the display itself is a bunch of LEDs. So the LEDs, in this case, like this one here, is labeled A, represents that LED there. So this one here, which would be D, would represent this LED here. So you get the idea that every one on our display is actually wired the way it is down here. So this is wired down here in order to provide those LEDs the proper location. So they're placed in the right location, and they're wired up the way we see down here at the bottom. Now the nice thing about this is we have only one wire called the anode, and you remember, so the anode here basically is there to provide a common power source. So in this particular case, since the diodes are common anode, your power would come in this way, right? And it would drive all of the LEDs that you have in your design, okay? So the power comes in the anode, and then on the other ends, you would tie them to ground to get them to light when the power comes in. So that's how the basic system is set up. So this is what's inside this particular element here. Now, with that being said, how do we wire it up? And remember, when we're talking about low-level design in hardware, we have to understand kind of how the hardware works and how it's interfaced. So if we look closely at the 7-segment display, we'll see that the anode is actually connected to power through a transistor. Notice very carefully, this is a PNP, not an NPN. So the PNP transistor would be activated with the anode going to ground here. So we drive the anode to ground. It's going to cause the transistor to conduct and turn on. And once that happens, it's going to mean that this has power along this bus right here. And that means that all we have to do to activate a particular LED is to activate and tie this line to ground, okay, and this line to ground. Now there's some important elements here that we want to remember. We have a whole series of resistors here whose main purpose is to limit the current and protect the pins on our chips, right? So remember, if you short this to ground, you're shorting power to ground. So you have to have a resistor to actually help prevent that from damaging the pin. Same thing here, when you short this to ground, right here, well, we would short it here. We go through a resistor in order to make sure that it doesn't overcurrent the input and damage the input. The resistor values will depend heavily on what type of LEDs you have, and it varies, although there's some people that like to standardize around 270, 300 ohm for the LED elements here. It really does depend on the type of device you're using, the type of transistor you're using, as well as the type of LEDs that are going to be used inside your device. Okay, so that's kind of how this thing works for one LED. That's just one LED. Now we're talking about interfacing multiple LEDs, so if we're going to, or multiple 7-segment displays, so if we're going to do that, we have to wire those up a little bit differently. Not much though, it's very similar. Remember what we said, each LED can be activated by activating the anode. Before we move on though, I want to point out that if this is tied to a pin, okay, so if this is tied to a pin, a port pin, then that port pin is pulled low and it goes to ground, right? Well, that means that you write a low value or a 0 to that particular pin on your hardware to activate this. So it's active low. That's what we call an active low anode. To turn on an LED, you have to not only activate the anode, you also have to activate the individual segment for that anode. So we activate the anode and we also activate the segment for each one in the display. And so those also are active low. So you turn on the LED by writing a low, and it's because of the way it's wired. Okay, this is the way this was designed and wired up. So a lot of people are used to saying, well, gosh, you turn it on with a 1, you turn it off with a 0. That's just simply not the case when it comes to hardware interfacing. It really depends on the hardware design and what the elements are that you're using. So in this case, active low here and active low there. All right, with that in mind, let's see if we can expand this to 4 displays. Now you'll notice this is very similar to the ones we did before. I do want to point out this very important notes here, this note here and this note here. Basically, I've not shown the current limiting resistors because it just clutters the diagram, but I made a note so you know that this is not directly connected to your port pins. If you do that, you'll damage your chip and it'll cost you lots of money and heartache. So don't do that. Make sure you've got those resistors there. I just left them off to make the diagram a little bit easier to read. So right now, since we have 4 displays, like here, we're not only going to have, the 7 segments that are shared between all of the displays, we're also going to have 4 independent lines that feed to the controller to tell us to turn on one at a time. So we'll turn on one at a time. That one, maybe, and then this one, and then maybe this one, and then this one, and then back over here. So only one is active at a time on the anodes. We combine those into a nice little bus of 4 bits, and we number the bus bits down 0 down to 3. So notice in this particular arrangement, bit 0 of the anode bus corresponds to digit 0 on our display if we consider the digits numbered from right to left, which is typical for bit numbering. We might as well number our digits that way as well. So this is the interfacing diagram. This is kind of how things fit together in our design. And we have to understand that in order to understand how to write VHDL code to drive it and create this illusion of a continuous display. So to get us started, let's take a look at a block diagram. Now, I really want to make sure you understand something very, very important here. Even though this is a design example video and we're showing you how to go through and design this thing. This did not come together in an instant. Okay, so this did not come together in 5 minutes. Okay, this took a lot of thought and process. This happens with time. So when you're designing, the first thing you would do is you would determine. Definitely need to improve the resolution there. Sorry about that. I'll fix that on the slides. But it's good enough to where we can, I think, read the digits. This is digit 1, digit 3, 0 to 3. These are our inputs. So what we've done is we've set up a design for our driver where we can feed it 4 4-bit values, and each one drives one of the digits. Because from the user point of view, the user doesn't really care about how the things work on the inside when you convert it to 7 segments using a 7-segment driver, that kind of stuff. They just care about displaying their numbers. And so since these digits typically display values between 0 and if you're into hex, goes up to Fox, or 0 to 9 if you're just doing a standard decimal display, we can use 4 bits, and those 4 bits will represent a value on the input. And so this value could be, for instance, this could be, and this is basically, I'll rewrite this since they're not showing up great, but this could be like digit 3, and this is digit 0, and this is digit 1, and then this is digit 2. Okay, so these are inputs to our system that someone using our component would apply in order to display the values. They would also need to apply a reset and a clock. Since this is a synchronous system, it means that everything is synchronized to the same clock. And if we have synchronous elements, we want to reset them to make sure our system comes up in a known state. So we've got our reset line feeding in, and then we've got our clock line feeding in. And then on the other side, we also providing, this is kind of a fancy LCD or 7-segment display driver. Fancy because I've added some extra features, which is individual blanking control. So if you activate one of the blanking inputs, like this one here is blank 3 at the top, and this would be blank 0 at the bottom. So these are individual blanking controls. That means you can turn the display off so that it doesn't display anything, right? So this blanking control can really create some nice, clean-looking displays. Like if you're trying to display the number 3, you don't want to display, 0003. That clutters the diagram and makes it harder to read. You'll blank those leading zeros out so that you just see the number 3 in there. And so by providing this in our design, we give the designer who's using our component the flexibility of making those blanks. The outputs here, this is 7 segs, and then this would be anodes down here. So there's your anodes, and these are the 7-segment outputs, and so those drive directly the circuit we saw over here. Remember, this is our 7 segs, and this is our anodes, and so we're driving those with our component. So this is an interface between a user of our system and the actual hardware. So this is called, basically, that's why we use the term driver. This is a driver for our multiplex display. Interestingly enough, everything inside is pretty straightforward. It looks simple once you see the design, but the process of coming up with designs is a complex thing. It's not something that, like I said earlier, happens overnight. You just don't pop in your head, the way you see it in the movies where, the engineer or scientist comes into the room and instantly knows the answer and writes it down in 5 minutes is hogwash. That's not how engineering works, and that's not how science works. It takes oftentimes, lots of effort and time doing the designing, analyzing what you have, trying to figure out what's best, what's the most optimal arrangement of the different components, and that can take, depending on the complexity, can take weeks, months, even years, depending on what you're trying to do. In this particular case, designing this took me, I don't know, maybe an hour of sitting down and thinking out the way the things were going, but that's because I've got a lot of experience. For someone who's new to this, it could take multiple hours of laying it down and trying to figure out what you're doing. But eventually you'll gain enough experience to be able to do it yourself fairly quickly as well. So I want to point out a couple of things in here that are really important for the design. So let's kind of erase what we have here, so we can start over and look at the different individual components. Basically, we have two multiplexers that are part of the design, and the multiplexers select digits, right? So we want the multi-select, let's say we're on digit 3, right? So we're going to display digit 3, which is the far left digit in our display. We want the multiplexer to have a number 3 on this input line and a 3 there, so that it activates this particular signal, passes it through our converter to convert it to 7 segs, and then drives the 7-segment output pins. We also want the blanking input to feed into our anode selector that comes out here, which is also identified with the value of 3 to tell it which anode to do. Remember, anodes are numbered 0, 1, 2, and 3, so we have to pick the right anode. So there are 3 things happening in this design. We are picking the proper blanking input, we are picking the proper digit input, and we are picking the proper anode to activate in order to display that number. And that picking, the process of selecting that particular element, is all up to this bad boy right there, okay? This is our digit count, and it's a simple counter that counts between 0 and, oops, that's wrong. It counts between 0 and 3, okay? And then it loops back around and counts to 0 again. So this is a counter that continually goes 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And the whole idea is it's constantly scanning the display and displaying the particular digit. It's constantly switching between these different inputs and simultaneously switching between the blanking inputs and simultaneously driving the appropriate anodes, all coordinated with this one signal here, digit select. Okay, so this is the one signal that coordinates the activity for all of these things. And that's an important distinction. That's an important thing to remember here, okay? So with that in mind, we have now a nice basic system that will take our input values here and display them on the appropriate display and handle all of the multiplexing and stuff internally. So all of that's handled internally by our system, and we don't have to worry or think about it too much, right? Because it's constantly scanning through and displaying the proper values. And that's excellent. All right, and so because of that, there's one more thing that we need to talk about that's important for our display, and that is this element here. Now, of course, if we're going to be multiplexing and we're going to be displaying these digits at a 1 kilohertz rate, in other words, every time a clock cycle for a 1 kilohertz clock activates, we want to pick a new digit. So if we're going to do it that way, then we want to make sure to create a scan pulse that tells us when to go next, okay? So we're creating this enable signal, okay, that enables the counter to count, and we only have it enable with a quick pulse like this. So it's a quick 1 cycle pulse that occurs every cycle for 1 kilohertz. So whatever a 1 kilohertz rate is, it's going to pop in every 1 kilohertz. But it's only a small system clock cycle pulse. That's all. So it's a 1 system-wide cycle pulse. This is being driven in this particular case with a 100 megahertz clock. So that's much faster than we can do our display with. And it won't actually light up our displays if we try to do it at this rate. So what we want to do is basically slow it down so that now we just, every 1 kilohertz, it will switch to the new display. So it enables the count. Now notice the common clock in here. Okay, so we have a common clock in our design. This clock and this clock are tied together. They're common. They're both being triggered at 100 megahertz. This is an enable signal that we are using in our design to enable the clock to activate. So it's basically causing the clock to be paid attention to or not. So if that enable is not active, the clock has no effect. If that enable is active, then the clock will do what we want it to do, in this case, count up to the next digit. So that enable is an incredibly important signal. So if we have our clock coming in like this, our enable pulse is going to look like this. Okay, so it's just going to be a short pulse but that's going to occur at a rate similar to every 1 kilohertz. Okay, so this represents a period of 1 kilohertz for a 1 kilohertz cycle. Now, with that in mind, and this is how this thing is working, let's take a look at some waveform diagrams. Now, one of the things that I've done here is, and this is really important in digital, is waveforms are incredibly important for a digital design, that you show how waves relate and interact with one another. And so in this particular case, I've only picked out a few, and I've also done something that's important for you to recognize. This is not 100 megahertz. So in order to show this in a more realistic way, I've decided to pretend the clock is very, 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 very slow. In fact, it's 3 cycles of the clock will cause a pulse on our enable count. So remember, the enable count basically causes the system to work and advance to the next system. So when the enable count goes high, it's really setting up what happens at the next clock cycle. So everything is still driven by the clock, but the enable pulse is what tells us the clock is activating it. So this enable going high means, oh, okay, so since count enable was high when that occurred, then digit select goes up to the next digit. That means instead of digit 0, I'll be displaying digit 1 in this case. Since I'm displaying digit 1, anode 1 activates here, but all the other anodes are inactive until, of course, the next clock cycle where this is activated. And that occurs, that occurs here. And then it goes to 2, and then digit 2, and then digit 2 down here is activated with an active low on the anode 2. All right, so, and it continues to cycle through this over and over and over again. This is the way in which our system works. This is the way everything comes together in our design. So we've seen the block diagram of how everything fits together, and we've seen the waveform diagram of how everything works on a timing level. Let's start looking at some of the code. So we're going to take a look at a couple of elements of the code. The important elements, since we've already talked about combinational logic, you guys know this. This is going to be a selected signal assignment statement. This will be a selected signal assignment statement. And this is combinational logic and can probably be done with another combinational logic, either a process or conditional signal or something like that. And so can this. This is selected signal assignment statement. These are combinational logic, easy to handle with some of the basic tools we have. This is where we're focusing our attention right now. Since we're talking about sequential systems and we're learning how sequential systems work, we want to focus on these 2 elements here, the one that generates the scan rate and the one that does the counting for us. So let's take a look at the scan rate first and see how we implement that. Now, the scan rate process basically creates an internal variable called count that keeps track of the frequency. Remember, the scan rate is the one that's generating this, with a clock frequency coming in like this, it generates this pulse every 1 kilohertz, right? So that's the purpose of the scan rate generator. And so what we're going to do is we're going to have a count that has been set up in our constants at the top that tells us how many cycles to go in order to do this. And we're going to count from 0 to that value. And once we've reached the value, Then we're going to activate the enable pulse and cause that enable to happen so that it drives the rest of the system. All right. So this part of the design, this initial piece here, is responsible for managing the count. That's our sequential piece. This is really a combinational piece that's inside the process. And it's combinational because it really depends entirely on the count value as to whether it activates or doesn't activate, right? The only time it's going to activate is if the count is equal to the 1 kilohertz count value. Then it enables the count. Otherwise, the count is not active. Now remember, signals that are assigned in processes do not get updated until the end of the process. So by doing this initial assignment of not active, we're not really affecting the output at all. We're basically saying, okay, the default value is this, and then we'll check to see this exception condition, which if it is the count, then we're going to activate that pulse for that one cycle. Then when it comes back the next time and it just says, hey, it is the count, it'll reset the counter to 0 and then start the whole process all over again. And so that's kind of how that works. So we separated out the sequential pieces here from the combinational pieces. Now there's another advantage for doing this declaration here this way. Okay, so like I said before, what I did at first was I came in and I said, all right, the enable count is not active. By doing that, we are assigning a value to a signal no matter what, whenever the process is activated, right? And this means everything that's activating it, whether the clock is rising or whether the clock is falling. But notice that it really doesn't depend on those at all. It doesn't depend on reset or clock. It really depends entirely on whether or not this count value is equal to that value as to whether it goes off or on. And so this is purely combinational logic down here, and up here is the sequential logic part of the process right here. So fairly simple, very common technique used for creating control signals inside your VHDL design in order to control various processes. So let's take a look at the next one, which is our counter. And this is pretty straightforward too. I chose to use unsigned type just to show you how to use an unsigned type in a design. I typically would normally use an integer here because it fits really nicely, but when we're learning, I like to show different techniques to use in here. So basically we initialize at reset to 0, and then whenever the rising edge occurs, if the enable count is active, remember the enable count is waiting. It's waiting for that edge, right? So if the enable count is active here, it waits for that next edge in order to trigger it. And so when the enable count is active, then I change digit select and say digit select equals digit select plus 1. And that's why this is happening here. Like there's the enable count active, there's the edge, boom, digit select is changed, right? So same here, sorry, wrong one. Let's go here. Digit select changes, all right? So and that's when digit select gets changed. All right, hold on there. There we go. And so that's how the digital count process works. So I've included in the slides the entire program showing the full commenting and the various elements in there for you to review. We won't go over that here because this is really, we're really primarily focused on, sorry, let's do the scrolling direction differently. We're really focused primarily on the sequential elements of our system and how to tie that together. But you can take a look here and notice there's your comment blocks here. This is your port declaration where we have our digits and then our blanking inputs, and there's our 7-second anode outputs. We set up our constants for our conversions to the 7-segment display. So we've got, this is our normal 7-segment display constants right there. We've set up internal signals, and those are all the internal signals in our design, such as enable counts, the selected blank, the selected digit, and then the digit select, which is actually that unsigned value that we were talking about before. Let's see, what else do we have here? That's right, so this now we get into the binary to 7-segment converter, pretty standard. We've seen that in earlier examples. We've got the digit select, which is basically just a multiplexer that selects a digit based on what the input value is. Blank select, same exact thing, that's the multiplexer in our design. And then anode select, this is a little more complex, but the anode select uses the digit select to determine whether or not to turn on the anode line. And you'll notice the very first condition is, hey, if the selected blank is active, in other words, if it's blanking this input, it basically doesn't display a digit. Otherwise, it takes a look at the digit select value to determine which one of the anodes to activate. And that's all our combinational logic. And here is the scan rate, and here is the, this is the digit count, and that's the scan rate process that we just talked about. So I think it helps, or I hope it did, going through a full design so you can see how designing a more complex sequential system works, how you can draw things out and sketch things out in block diagrams so you can see how all the elements fit together. And you can create a very nice hardware design in a very short time, very little code necessary to do something what I consider fairly complex can be done in a very small amount of code. All right, well, that's it for this time. I hope you enjoyed going through our little design. Thanks a lot, and we'll see you in the next video.